Hi all, welcome to our 6th lecture now for CHY 113. Sorry there's no special guest to start this lecture off like there was last time. Little Henry is at daycare today, dazzling all of his teachers there with his cuteness, I am sure, and giving his mom and dad a chance to get some work done today. And so with that, let's go ahead and jump right into our warm-up questions. And so we'll start with this one here, and go ahead and perform these following conversions that we had went over last time. So pause the video and see what you can come up with to convert all of these different units. And hopefully this is what you came up with. Secondly, given the following percent compositions, so this is a compound that contains only carbon, hydrogen, and oxygen. You're given the percentage of carbon and the percentage of hydrogen, told the rest of it is oxygen, and so find the empirical formula of this compound. Hopefully you were able to come up with C2H6O. Now as a follow-up to that, given this empirical formula, let's say you're told that the molar mass of the actual compound is 138.21 grams per mole. Using that, find the actual molecular formula for this unknown compound. And hopefully you were able to come up with C6H18O3. And if need be, go back and remind yourself of the difference between empirical and molecular formulas. And so let's go ahead now then and jump into our new material, starting to look at chemical reactions. So when we look at chemical reactions, one of the biggest things to keep in mind is that what we're doing is taking the compounds that we had initially, the elements and or compounds, and they're going to come apart and then come back together in completely different ways. And so we're looking at the process by which a chemical change will occur. Remember, chemical change is when we have a brand new substance that didn't exist before the change occurred. So a chemical reaction is how a chemical change will take place. And so there are lots and lots and lots of different aspects of chemical reactions that we're going to begin to look at today. And so the big topics, big concepts that we're going to explore today, sort of an introduction to chemical equations in general. We'll look at balancing chemical reactions and chemical equations in order to satisfy the law of conservation of mass. And then we'll look at what we call aqueous solutions. And so look at reactions that are taking place with compounds that are dissolved in water, where most of our reactions do occur. And then finally, we'll start to look at one particular type of reaction today. We'll look at precipitation reactions. And so before we get too deep, one thing that we do have to recognize that will start to be pretty key for us is the existence of what we call diatomic molecules. Diatomic molecules are elements that, when they are existing in isolation, when they're existing by themselves, they always exist as one atom of that element bonded to another atom of that element. And you can see them all listed here, all the elements that will do that. And so the oxygen that we breathe, for instance, when we're breathing in oxygen, that oxygen is not just in the form of individual oxygen atoms floating around. It's all in the form of O2, one oxygen bound to another one. The nitrogen in the atmosphere, under the general atmosphere, is roughly 80% nitrogen. All of that nitrogen is in the form of one nitrogen atom bonded to another one. And so we have to remember that. And this is a list that you are going to have to just, another list, unfortunately, that you'll have to know and to memorize that this occurs. Because when things do get mixed up and we form new compounds, we have to remember that if a reaction is occurring where we end up getting one of these compounds by itself, then it has to exist in this way. It has to exist as for instance, O2. Just as a real quick general example. And we're going to look at sort of the nature of reactions and how we would do this sort of reaction in a little bit. But let's say we have something like sodium oxide reacting with chlorine. First of all, we know that the chlorine, it's by itself. Chlorine is one of our diatomics, so it would have to exist as Cl2. And so that tells us that our chlorine here has to be written as Cl2 because that's how it's going to exist. Now again, we'll look at some of the specifics of a reaction like this in a minute, but what's going to happen is this is called a displacement reaction where the chlorine is going to come and kick out the oxygen. And so sodium is going to come together with the chlorine then. When it does that, we use the rules that we learned about last time, a couple lectures ago. We know that sodium has a 1 plus charge, chlorine has a 1 minus charge, and so when they come together now to form a new compound, the formula for that is going to be NaCl. Oxygen now has been kicked out and it's by itself. But when oxygen exists by itself, it exists as O2. And so we would have to reflect that here as O2. And so that's why it's so important to be able to recognize these diatomic molecules so that you know that something like chlorine is going to exist as Cl2 over here in our reactant side. And then when oxygen ends up by itself in our product side, it has to exist as O2. And we'll look at more of this in a little bit, how we actually remix the compounds when they come back together and so on. But I just wanted to point out this example to show why we have to know these diatomic molecules and which molecules do exist diatomically like this. And so let's start off, though, just looking at some basics of chemical equations. So we could describe something easy enough with words. We could say, for instance, that methane reacts with oxygen to then yield carbon dioxide and water. A chemical equation, though, now gives us a symbolic representation of that reaction. We would say our CH4 plus our O2. So here's our methane reacting with our oxygen right here. These are the reactants of our reaction. The CH4 plus the O2. Don't worry too much about these numbers in front, these coefficients in front of the oxygen and the water. We're going to talk about those in a little bit and where those come from. But the methane reacts with oxygen, so there are reactants. To yield, that's what the arrow is. The arrow is just saying that these are reactants react together to yield our products, which are carbon dioxide and water. And so our reactants react to yield our products. And so this chemical equation then just gives us a way to symbolize with the elemental symbols what's actually going on. We do often add in some additional information, a little bit more detail. We quite often include the states of matter that the compounds are in. And so CH4 is natural gas, methane, that's usually going to be in the gas phase in what we call normal atmospheric conditions, reacting with oxygen, which would also be in the gas phase, producing carbon dioxide, which would be in the gas phase, and then typically liquid water would be produced too. So that's a lowercase L right here. It's not the number 1. And so the typical states that we would see, S for a solid, L for a liquid, G for a gas, and AQ for aqueous, which we'll discuss in more detail later. But aqueous means that the substance is dissolved in water. Now note that that is very different from the substance being a liquid. And so as an example there, just to illustrate the difference for you, if I have, so NaCl, liquid, this means that I have actual, I took salt, I took solid NaCl, and I heated it up to the point that it melted to become a liquid. That is a lot different than saying I have NaCl aqueous, which means that now I've taken that salt, I've taken the NaCl ionic compound and dissolved it in water. So a big difference between those two notations, between liquid and aqueous. Aqueous always means that we have dissolved the substance in water. And so our chemical reactions, or our chemical equations, show us our reactants and our products. Excuse me. They also show us the relative amounts that are used in a chemical reaction. And those are the numbers in front. And we'll see where those come from in just a minute. But for instance, in this equation here, the formation of aluminum oxide, we need to take 4 aluminum atoms. We need to add 3 oxygen molecules to that. and that's going to form 2 aluminum oxide molecules. And these numbers in front are called stoichiometric coefficients. Don't necessarily worry about the word stoichiometric quite yet. We're going to talk a lot more about stoichiometry in the beginning of Unit 2, so in a couple of weeks. But for now, definitely focus in on these numbers in front, the 4, the 3, and the 2 here. Those are coefficients. And so that is very different from the subscripts that we use in the chemical formulas. And so that's just more terminology that we have to be aware of, the difference between coefficients that come out in front of the compounds or the subscripts which are built into the chemical formulas. Let's talk about where those coefficients come from, though. And so the law of conservation of matter tells us that mass cannot be created or destroyed through the course of a chemical reaction. And so since the same number of atoms are present in the beginning of a reaction and at the end, the amount of matter is not going to actually change. Or think about that in reverse. Since the amount of matter does not change, since we have the same amount of matter in the beginning of a reaction as we have at the end of a reaction, that means that the number of atoms that we had cannot change. We can't add or subtract atoms from one side of the reaction to another. And so a great example of this is here we have the decomposition of mercury oxide. And so we take HgO. So mercury oxide, not going to worry about the states of matter for this little demonstration. So it's going to decompose. A decomposition reaction is when the 2 elements are going to just split apart. And so it's going to split apart into mercury and oxygen. We have to remember, though, that oxygen is one of our diatomic molecules. So when the oxygen is separated from the mercury, what that is going to do is then we're going to have mercury, which is not one of our diatomics, so we can just write it as Hg. But oxygen is now by itself, it has to be O2. And so the question is, where did that additional oxygen come from? And so if we sort of write this out more, looking at these as Hg bonded to an O, they break apart to form Hg plus O bonded to O. And so here we have, in our initial compound, we started with mercury oxide with just 1 oxygen, but because of the way oxygen has to exist when it's by itself, it has to exist diatomically as O2. That additional oxygen could not have come from nowhere. We can't just materialize it because that violates the law of conservation of mass. What we can do, however, is say that we started with 2, actually, let me do that in a different way. We could say that we started with 2 of that entire molecule. That gets us to the 2 oxygens that we would have had to start with in order to end up with our 2 oxygens. That leads us to another problem. You can see now that we're actually starting with 2 mercury atoms, right? We're starting with 1 mercury atom in this one and 1 mercury atom in here, but we only end up with 1. And so the way that we would solve for that is to say, well, we're not just going to make 1, we're going to have 2 at the end. And so now we have not violated the law of conservation of mass. If we look at this overall depiction right here, we're starting with 2 mercury atoms. We have 2 mercury atoms at the end. We're starting with 2 oxygen atoms. We have 2 oxygen atoms at the end. And that's what the coefficients in front are all about. Now we have a chemical equation that does not violate the law of conservation of mass. And so that's called balancing a chemical equation. In order to balance a chemical equation, you have to put numbers in front as coefficients in order to have the same number of each type of element on both sides of your equation. Now let's look at some other examples, or let's clarify some things. So here we have the formation of water. And so hydrogen and oxygen are both 2 of our diatomic molecules. And so when they're existing by themselves, they have to exist as H2 and O2. And so H2 and O2 come together to form water, and we know the chemical equation of water is H2O. And so we have to look to see if this is balanced. And so to do so, we're going to look to see, do we have the same number of each element on both sides? We see that we have 2 H atoms in our reactant side, and we have 2 O atoms. In our product side, we have 2 H atoms, but only 1 oxygen. And so the oxygen atoms are not balanced. Now, what you're going to be very tempted to do is to just go ahead and do something like this. Let's just put a subscript on that O. Let's make it H2O2. Now it's balanced, right? Now I've got 2 of each on each side. Everything's balanced, and I'm very happy. No, 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 no. H2O2 is a completely different molecule. H2O2 is hydrogen peroxide. If I wanted an equation for the formation of hydrogen peroxide, then absolutely, this is what I would have, and I'd be good to go. But our chemical equation that we're looking for is describing the formation of water. Water has a formula of H2O. So you cannot modify that. Once you modify it, it's something new. It's something different. And so once we know what our subscripts are, once we've figured out our chemical formulas for our products and our reactants, rather, once we have our correct chemical formulas, we cannot simply adjust the subscripts in order to balance the equation. We cannot change what the actual molecule is. What we can change is how many of them we have. And so let's look at how we would go about that with this example. And so we know that we need to have 2 oxygen atoms on the right-hand side of our molecule. We need to have 2 oxygen atoms for our products. The way we're going to accomplish that is by saying that we create 2 entire water molecules. Now I have 2 oxygen atoms because I have 2 H2Os. And so remember what that really looks like. What I'm saying is that we have what we've formed. So let's sort of just write it out like this. So H plus O2 forms H2O. And so what I'm saying is that we've now formed 2 H2Os. So we formed 2 of the water molecules. Hopefully you can see the issue that we now have, though. 1, 2, 3, 4 hydrogens, and only 2 hydrogens in our reactant side. So the equation is still not balanced. And so what I'm going to do is to balance that by having 2 H2 molecules to start. So instead of just this 1 H2, I'm going to say that I have 2 of them to start out with. And so we have 2 H2s plus 1 O2 gives us 2 H2Os. Now I have the same number of each type of element on each side. I have a correctly balanced chemical equation. There we go. So let's look at a couple of practice examples. So we're going to run through the same thing. This would be what we call a double displacement reaction. We have NaCl plus MgBr, MgBr2 rather, react to form NaBr plus MgCl2, or in words, sodium chloride plus magnesium bromide, react to form sodium bromide plus magnesium chloride. And so we start by a simple counting. And so we can see everything that we have here. I'm just counting up each type of atom. Now again, what you're going to be tempted to possibly do is something like this. Cannot do that. Think of everything that we learned a couple lectures ago with how we come up with chemical formulas. NaCl2 is not how sodium and chloride are going to come together. NaBr2 is not how those are going to come together. And so we have to remember all those rules that we talked about as far as how ionic compounds are going to form. And so what you're starting to see is just how much stuff in this course is going to build on itself. If you are still thrown off, or if you're still having trouble with writing ionic formulas and coming up with ionic formulas, you're going to struggle through a lot of what we talk about today until you master that concept. And so that's one of the reasons why it is so important to stay current and not fall behind in a class like this, because it's going to build and it's going to snowball. And so we know then that we can't do this. We can't simply add our 2's there as subscripts. What I can do, though, is say that I'm going to start with 2 NaCl's, and I'm going to create 2 NaBr's. Now I have a correctly balanced chemical equation. 2 sodiums on each side, 1 magnesium on each side, 2 Cl's on each side, 2 Br's on each side. I have a balanced equation. And so just to reiterate those rules, once the equation is written, once you have figured out the products and the reactants, the subscripts cannot change. Do not change those subscripts. Instead, in order to satisfy the law of conservation of mass, coefficients are used to balance our equations. And so here's an example like we had looked at earlier. Our CH4, our methane, plus our O2 react to form carbon dioxide and water. So let's look to see how we might balance that. So some of our rules as far as balancing chemical equations go, or some of the steps that you want to think about, is generally speaking, we're going to write out our entire equation, usually including the physical states. Generally, as you do more of these, you'll come up with sort of your own patterns and your own process. But as you're first starting out balancing equations, what I would recommend is balancing the compound with the most elements in the formula first. And so if you have something like earlier with the CH4, maybe balance that hydrogen first and then go from there. Anything that's on its own, wait till last. And so something like the O2 from before, wait and balance the oxygen for the last thing that you do. Because what you're going to find as you balance equations, just like we've seen a couple times already, is quite often you're going to put a coefficient in front of one thing, and that's going to mess something else up that you have to then go fix. And you might go back and forth with that a couple of times until finally everything now balances out. And so as you're going through that process, if you save something that's by itself until very last, then you know that adjusting for that isn't going to mess anything up that you have to worry about. And then do some checks. Make sure that that everything does at the end count, and make sure that you have the same number of each type of element on both sides. It sounds like I'm being sarcastic and being a jerk when I say this, but some of you are going to meet with me during office hours about some of this, and you're going to balance an equation and ask me to check it and say, is this right? My response to you is going to be simply count. Count your elements on both sides of the reaction. If you have the same number of elements for each type of element, if you have the same number on both sides, then you're good to go. If you do not have the same number on both sides, you've done something wrong. Try to track it down. And lastly, just like for ionic formulas, if the coefficients could be simplified in some way, then we do that. In a chemical reaction, we always describe the lowest possible number. And so just as an example with a very general reaction, if you come up with something that's like 3A plus 6B forms 12C, then you would simplify this down eventually. You would get to A, dividing everything by 3 plus 2B makes 4C. And so you would just simplify it down if you run into a situation like this, which might happen. Quite often, you'll also find that balancing equations is a matter of trial and error. And so pick something and fix it. Pick one of the elements in there and adjust your coefficients so that it takes care of that element. See what that did to anything else in the equation, fix that, and sort of keep going back and forth that way. And so remember that as you're doing this, each side of the chemical equation must have the same number and the same type of each atom. It has to all add up. And so here's an example. So we have calcium carbonate decomposing to form calcium oxide and CO2. So we go through first and we count. We have 1 calcium on the reactant side, 1 in the product side, 1 carbon on each side. We've got 3 oxygens on each side. And so this one, we don't have to do anything to. Oop. This one is balanced as it's written. And you'll find that sometimes, that when you go through and analyze everything, the equation was balanced just as it was written. You didn't have to adjust anything. And that was our case here. Here, though, we have a formula or an equation describing the combustion of ethane. So C2H6 plus O2 gives us CO2 plus H2O. So we go through and we start our counting. 2 carbons and 6 hydrogens and 2 oxygens in our reactant side. Just 1 carbon, 2 oxygens, 2 hydrogens, or sorry, 1 carbon and 3 oxygens total, and 2 hydrogens on our product side. So oxygen is by itself. Let's save that for last. We can see O by itself right here. And so we're not going to fix that one right off. We're going to save oxygen for our last element that we actually balance. And so instead, let's go ahead and start with hydrogen in this example, because that's the one that we have the most of. We have 6 hydrogens here, 2 here. So let's go ahead and fix that by putting a 3 in front of our H2O. Now that gives us 6 hydrogens in our product side, and we have 6 hydrogens in our reactant side. Because remember, that's 3 of the entire H2O molecule. So each H2O has 2 H's. So if I have 3 of those, I've got 2, 4, 6 total. We do run into a problem here. You'll see this sometimes when you're balancing equations, especially this type of combustion reaction. We see after we've put our 3 here, our reactant side over here is always going to have an even number of oxygens. Doesn't matter what we do, no matter what number we put here, we're going to have an even number of oxygen atoms. That's a problem because now we have 2 here and 3 here. We have 5 oxygen atoms. With this 3, we can never have anything except an odd number of hydrogens over on our product side. Sorry, of oxygens on our product side. And so that does present us with an issue. That presents us with a bit of a problem. If you do run into that, if you recognize that situation, then go ahead and just double your number there. Make it that 6 H2Os instead. Now, though, we have to recognize that what we've done is now we have 6 times 2. We have 12 hydrogens over here on our product side. And 6 over here, so we're going to fix that with a 2. And so this is where we're at so far. We're doing our counting. And so let's go ahead and balance our carbon next. So we can see that we've got 4 carbons over here on our reactant side, only 1 here on our product side. So we're going to put a 4 in front of our carbon dioxide, 4 CO2s. Finally, we're going to balance our oxygen. We can see that we have 8 plus 6 is 14 oxygens. Remember, this is O2. So in order to get to 14 oxygens, I need 7 O2 molecules. Now I do my final count, and it all works out. I have the same number of each type of element on both sides. This is just going through that again, looking at it in a slightly different way. And so we're going to run through it the same way that we did before. Look, doing our counting of each type of element, we see that things are not balanced. And so maybe in a slightly different approach, we're going to take care of our biggest molecule first, our C2H6. And so in order to fix that on each side, we're going to have 2 CO2s and 3 H2Os. And hopefully you can see where that would come from. Now, what we do is we see, okay, and that gives us our 2 carbons, our 6 hydrogens, it gives us 2 and 7 oxygens. What you would possibly be tempted to do, what you can do as an intermediate step, is if I have 7 oxygens over here on my product side, remembering that this is O2 on our reactant side, if I could somehow have 3.5 O2s, that would take care of it, right? That would take care of my balancing for me. It is okay as you're balancing, and again, this is the same as the one that we just did. It's just a different approach. It is okay to do this as long as you recognize that this is an intermediate step. When you get to this point, if you're saying to yourself, oh, if I could just put 3.5 there, if I could put something and a half, that would take care of my balancing form. If you get to that point, that's fine. Put it there, but then just go ahead and go through and double everything. And that will lead you to the balanced equation. And so remembering, like I said before, because I can't reiterate this enough, that we can only ever change our coefficients. You might be tempted to put a 2 there. Do not do it. I will slap your hand with a ruler. I will not really do that. For one thing, I'm in a video, and secondly, that's pretty illegal. But I would really be tempted to slap you with a ruler if I could. Cannot change those subscripts. You can add coefficients in front, and that balances our equation. So go ahead and run through these as a practice. Try to come up with these different, try to come up with the correct balancing for these different chemical equations. And hopefully what you came up with is the following. If not, go back and practice. And again, I know it sounds like I'm being a sarcastic jerk, but literally go back through and count and see where you went wrong. See what doesn't add up on each side. If you did not get these answers, then I guarantee that something didn't add up. Maybe you forgot your 2 right here. And so you would go back through and you would say, oh, well, now I only have 1 N over here and I've got 2 over here. So that obviously doesn't work. I've got 6 H's over here, but now I only had 3 over here without that 2. So literally just if you miss these, go back through and count and see where you missed, see which atom you did not have balanced. Now, as I mentioned earlier, most of our reactions that we talk about are going to take place in solution. They're going to take place in water. And so what we need to talk about then, or one of the things that we need to talk about, is what actually happens when a solid dissolves in water. Because it's not necessarily as simple as you might necessarily think. When something dissolves in water, we break it into 2 different categories. That substance is either going to be an electrolyte or a non-electrolyte. Electrolytes are going to be ionic substances which break up into their ions when they're in water. Non-electrolytes are typically molecular substances, covalent substances, which do not break into ions. And we can depict that, we can show that with what we call dissociation equations. And so, for instance, here, our lithium chloride solid. What I didn't put in all these arrows is dissolving in water. And so we would be adding all of these into water. When I take lithium chloride as a solid, it's an ionic substance. Remember, lithium here, very much a metal. Chlorine over here, very much a non-metal. So lithium chloride, an ionic substance. It's dissolving in water. When ionic substances dissolve into water, they're going to dissociate into their ions. And so what that means is once it's dissolved in water, I no longer have lithium and chlorine bound together. I have lithium ions and I have chloride ions now all floating around in there. They are going to separate, they're going to dissociate from each other. Magnesium chloride, MgCl2. It's an ionic substance. Magnesium, chlorine, metal and non-metal, going to separate into its ions. The thing to recognize here, and this is going to become important for some various things that we talk about later in the course, is that remember we've got 2 chlorines. And so in the dissociation equation, we represent that as being 2 chloride ions. Again, let's sort of just look at that pictorially. Is that a word? We're going to look at a picture of that. And so MgCl2 as a solid, it's going to split up into Mg2 plus ions, but also the chloride ions. We've got 2 of them in there. Now, all 3 of these are floating around as separate entities within the solution. So they're all separate from each other, all floating around and bouncing around in there. And so they are no longer bound together. They've dissociated from each other. Once again, we start to see the reason why it's so important to, or one of the reasons why it's so important to memorize your polyatomic ions. Here we have sodium phosphate, Na3PO4. Sodium phosphate is going to separate into its ions. PO4, as it exists as a polyatomic ion, is going to stay together. PO4 is not going to separate. And so we end up with our 3 Na plus ions and 1 of the PO4 3 minus ions. And so all 4 of those are now going to be floating around in the solution. And so again, if we just sort of take a look at what that really looks like so that you can really kind of see what's going on there. What I started with is something like this. And so all 3 NAs bound to the PO4. When that then dissociates into water, these are all separate from each other, all floating around in there. And remembering that the PO4 is staying together as its own entity. It's a polyatomic ion. It is not going to separate. So that's very important, very key for us. Lastly, we have sucrose, just some common table sugar, C12H22O11 as a solid. We dissolve that in water. Now that is not an ionic substance. All nonmetals in here. This is a molecular substance, therefore it is a non-electrolyte. It is not going to break up. It is actually going to stay together in its complete form. Let's actually bring up a quick image for you. I didn't put this into the PowerPoint, but it's one of the advantages I have of just working from my computer like this. Sucrose molecule. And so here, actually, I like this one right here. Here's an image of what sucrose actually looks like. And so there's a sucrose molecule. When this dissolves, this is what's actually going to be in the water. This whole thing is going to stay together when it's dissolved in water. Much later in the course, we'll talk about how that happens. We'll talk about the interactions that are going to occur between the water molecules and the elements within the sucrose molecule. But for now, we just have to know that since this is a non-electrolyte, since this is a molecular compound, this whole entire thing is going to stay together when we dissolve it in water. It's not going to break apart. Unlike our ionic substances, which are electrolytes, which will break up into their constituent ions. So very important distinction between the two. And so one thing to just note as well is that when we use the designation AQ, we use the designation aqueous. If I write MgCl2 parentheses AQ, that's the equivalent of writing broken up into its ions. And so it's understood that when I see this, that what I really have in water is this right here. Just because we know that this is something that is going to dissociate. We just don't always write it out as its constituent ions. We typically write it like this within a chemical equation, but it's understood that this is functionally what is actually going to exist. And so a couple of just differences between electrolytes and non-electrolytes. An electrolyte will conduct current. And so if you have, let's see if I can come up with my very crude drawing here. Let's say I have a battery, and that's going to flow out to a solution. Sorry, let me even do this. Here's my solution. Here's the battery flowing in. There's my solution there. And then we have another lead or another wire coming back out, leading down here to a very crude depiction of a light bulb, and then leading back to my battery. So just a very simple circuit. Now, if this solution here, so if my solution right here is an ionic solution, let's say I have some NaCl aqueous in here. So I've got a sodium chloride solution, ionic solution, it's an electrolyte. I connect this, and my light bulb's going to light up. As the solution itself will conduct electricity, and we'll have electricity flowing, so our light bulb can actually glow. Now, if on the other hand, I have a non-electrolyte solution in here, let's say I've got just a glucose solution, C6H12O6, aqueous, and I connect everything, light bulb stays dark. That solution is a non-electrolyte. It is not going to conduct electricity. Water, by the way, pure water. Let's say I just have this. So I haven't dissolved anything in there. I've just got pure water, non-electrolyte. Pure water is not going to conduct electricity. Now, maybe you're asking yourself, well, then how come I can't be in the lake during a thunderstorm? Or how come I really shouldn't drop my radio into the bathtub with me? Any water sample like that is not pure water. There's going to be ionic substances dissolved in there, which will enable the electricity to actually travel. And so pure water itself, if it's absolutely pure water, would not conduct electricity, or very, very, very weakly for reasons I would talk about later. But basically pure water, non-electrolyte, it won't conduct. So electrolytes do, however. They'll make our light bulb pop and glow for us. What we call a strong electrolyte means that 100% of it is going to dissociate into ions. And so, in other words, something like sodium chloride is a strong electrolyte, which means that if I have 100 NaCl molecules, 100 ACl units, it's going 100% of that, all of it is going to split up, which means that I'm going to have 100 of each type of ion in there. Weak electrolytes typically will end up being more molecules than ions. And so what I mean by that is something like, as an example, acetic acid. Acetic acid is a weak acid. It's a weak electrolyte, and these numbers are just for demonstration purposes. These wouldn't be the true numbers. But if you have 100 acetic acid units, you might only get one of those that splits into the H plus and the CH3COO minus, the acetate ion. The other 99 are going to remain as the molecular compound still bound together. Though, and we'll talk about the distinction there and how we tell the difference in a little bit between something that would be strong and something that would be weak. I will say for the most part that any substance that you recognize as ionic, any substances made up of a metal and a non-metal or a polyatomic ion, those are going to be strong electrolytes. A non-electrolyte, as I mentioned, does not conduct electricity. Water is an example of that. Not going to worry about that part of it. We're going to go now to, why isn't my next screen coming up? There it is. Okay. And so how do you tell? And so like I said, if you have something for a solute, if you have something that is dissolved into an aqueous solution, if it's an ionic compound, I'm going to try to make that thing so it doesn't come up. There we go. Nope, coming back. All right, if you have something that's an ionic compound, that is going to completely dissociate into its ions, and it's going to be a strong electrolyte. So just bar none. If it's something you recognize as ionic, it's going to be a strong electrolyte. If you have something that's a molecular compound, and so something that is covalent, most molecular compounds are going to be non-electrolytes. Some of them, however, acids and weak bases might fall into strong or possibly weak electrolytes. The way that you would tell is if you have a molecular compound that's an acid or a base, and we'll talk about how we tell acids and bases in another lecture. If it's a strong acid, it's going to be a strong electrolyte. If it's a weak acid or a weak base, or if it's a strong base even, rather, it's going to be a strong electrolyte as well. Weak acids and weak bases form weak electrolytes. And so acids and bases in general, if it's a molecular compound and it's an acid or a base, it will form electrolytes. The question is if those electrolytes are going to be strong or weak. Strong acids and bases form strong electrolytes. Weak acids and bases form weak electrolytes. Now, later on, we are going to talk more in detail about acids and bases. When we do get to there, the way that you'll differentiate between weak acids and strong acids and weak bases is unfortunately just a little more memorization. There are 6 strong acids and 6 strong bases, all listed here. All other acids and bases are weak, every single one. And we'll look a little bit more at acids and bases later, but we have already touched on it a little bit. Remember when we went over our naming, talked about how if you see hydrogen in the front of any of your acids, hydrogen in the front of a compound, that more than likely denotes an acid. And so perchloric acid, hydrochloric, and so forth, we have our hydrogens in front. And you can maybe see the similarity between all these bases. We'll talk about different types of bases a little bit later in the course, but all of the strong bases contain the hydroxide ion. Is that something else to look for? So let's just go through sort of a flow of how we would determine if something is conductive, if something is an electrolyte. You need to ask yourself, is it molecular or ionic? Is it covalent or ionic? And based on that, is it going to conduct electricity? And is it going to do so strongly, weakly, or is it a non-electrolyte? And finally, what's the best way to represent the dissolution of that compound when we dissolve it in water? So NaCl. We ask ourselves first, is it molecular or ionic? And we know that it is an ionic solution, which means that it's going to be a strong electrolyte, which means that we're going to represent it as Na plus and Cl minus. Sucrose, C6H12O6. Molecular or ionic? We know that one's molecular, made up of all nonmetals. That's going to make it a non-electrolyte because it's not an acid. It's not an acid or a base. We don't see hydrogen in front. We don't see any OH in there. And typically OHs, I know you see some O and you see some H in here. Typically with bases, you would see it written out as the OH together. And so we're on the lookout for that. And so our best representation for this when it dissolves in water is the whole thing is actually going to stick together. Finally, HCl. We ask ourselves, is it molecular or ionic? Now this one is made up of 2 nonmetals. So we would actually classify this as molecular according to the rules that you know that we've talked about. Hydrogen's a nonmetal, chlorine's a nonmetal. But we have to recognize that it is one of our acids, hydrogen in front with our chlorine. So this is hydrochloric acid. Hydrochloric acid is one of our strong acids. It tells us that it is going to be a strong electrolyte, and therefore we're going to represent it as such. Then finally, the same thing with NaOH. Now we see that OH, hydroxide. And in fact, NaOH is one of our strong bases. However, we can also tell that this is ionic because it's made up of our sodium ion, our Na+, and our OH, our hydroxide polyatomic ion. So it's ionic, which tells us it's going to be a strong electrolyte, and we're going to represent it as such. Last example, acetic acid. So again, there's our H in front. We know it's an acid. We know it's that actually this one would be molecular, made up of hydrogen and our acetate ion. Actually, this one, the distinction gets a little bit fuzzy. Don't worry too much about that. The important part is that it is an acid, but it is not one of our strong acids. It's not on our strong acid list. Therefore, we're going to represent it as staying mostly molecular. Actually, that wasn't the last one. NH3. I'll just go through this one fairly quickly. Hopefully, you're sort of catching on. That this one would end up that this one is molecular. Therefore, it's non-conducting. It's a non-electrolyte, and that's how we represent it. And so now let's actually start talking about reactions that are going to happen in solution. So that whole conversation, electrolytes versus non-electrolytes and breaking up into solution, is leading us now to discuss how elements and how compounds are going to dissolve in water and then react together when we mix them together. And so when we're looking at reactions, we have to predict what is going to actually happen in a reaction. And to do that, we have to recognize that there are several driving forces to reactions. There are several things that may occur that drive a reaction to even happen. Because sometimes you might mix two chemicals together, nothing happens at all. They just end up as being the two chemicals sitting there, and they don't actually react together whatsoever. Because there's nothing to give them an incentive to react. There's no driving force to that reaction. One of the driving forces that we look at is going to be the formation of a precipitate, the formation of an insoluble solid, and we'll see what that means in a bit. But it's basically when we mix, if we mix two things together, two liquids together, or two aqueous solutions together, a solid forms. And so we take something that is dissolved in water, something else dissolved in water, mix them together, and we end up getting a solid from that. That can drive a reaction. Maybe we take two things together and a gas forms. If you take a lot of different metals, but if you drop maybe some zinc, just pure zinc metal into a test tube and throw some hydrochloric acid on top of that, it's going to start to bubble. And those bubbles are the formation of hydrogen gas. And so that gas formation drives that reaction to occur. The formation of a weak electrolyte can drive a reaction. We'll talk more about that one in a little bit. We'll leave that one till the next lecture. We're going to focus, actually, the rest of today's lecture is going to be focused on this first one, on the formation of a precipitate. In order to figure out if a precipitate is going to form, we have to know if a compound is going to be soluble in water or not. And so all this that we've talked about, with electrolytes and non-electrolytes, an electrolyte will only form with an ionic substance if it's something that dissolves in water. Not all substances will dissolve. And so we have to know, we have to be able to figure out if a compound is going to be soluble, if it will dissolve in water or not. For molecular or for covalent compounds, the molecule itself must be polar. We're going to talk a lot more about polarity. It's actually one of the last topics that we talk about in the course. So for this discussion, we're going to focus on ionic compounds. The solubility of an ionic compound is governed by what we call a set of solubility rules. Now, as I go over these are going to be fairly complex. And you might be worrying, do you have to memorize them? You do not. I will allow you to use the solubility rules on your exams in this course. So you will be able to have a copy of this chart up in front of you as you are as you're doing your exams for this class. And so the way that this works is there are two different charts. We have this one here, which we'll go over in detail in just a second. This is our list of soluble compounds. And we have a list of insoluble compounds. And so when we're using the solubility chart, we sort of use it, well, what we do is we take a compound and we see what that compound contains, and we look to match that up with the appropriate solubility rule. And so, for instance, if I have sodium chloride, if I have NaCl, then I look and I see that, okay, Na, almost all salts, almost all compounds that contain Na are soluble. And so if sodium is my first ion listed in whatever compound I'm talking about, that compound is soluble in water. That compound will dissolve in water. Potassium. If potassium is my first ion listed, if ammonium, NH4 plus, is my first ion listed, those are going to be soluble compounds. They will dissolve in water. Any nitrates, anything that ends with NO3, any chlorates, any perchlorates, any acetates. And so anything containing any of these ions, if only one of these ions is in the compound that you're looking at, that compound is soluble in water. It will dissolve. Ionic substances that contain chlorine, chloride, bromide, or iodide, almost all of those are soluble. So almost all of those will dissolve when we drop them into water. There are some exceptions we start to see now, though. And so if we have any of these that contain silver, mercury, or lead, those are not soluble. So there are exceptions. And so, for instance, if I have, let's just look at some examples. See where my cutoff is. There I am. Okay. And so if I have something like, let's say CaBr2, calcium bromide. So I look at my solubility chart and I see, okay, bromide is in my soluble list. Almost all bromides are soluble. Calcium is not one of these exceptions. Therefore, calcium bromide is soluble. However, lead bromide, almost all bromides are soluble. Lead is one of the exceptions. That is not going to be soluble. So that would not dissolve in water. Silver chloride, not soluble, because silver is one of those exceptions. Magnesium chloride. Magnesium is not one of our exceptions, so it's soluble, and so forth. We would do the same for our list of fluorides, only now we just have a few more exceptions. And so for fluorides, most salts that have fluorides are soluble, except if your cation is magnesium, calcium, strontium, barium, or lead. So basically, if it's most any of the alkaline earth metals, or where's lead? Lost it. There we go. Or lead. Then it would not be soluble if it's a fluoride. Same with sulfates. If your anion is sulfate, SO4 2-, most of those are soluble, except if the cation is any of those that are listed. And so if you're trying to determine if a compound is soluble or not, then you would, again, identify what is the compound made of, and look for information on either of the solubility lists, either a soluble list or here's our insoluble list. And so, for instance, if I have a carbonate, if I have something that has carbonate in it, maybe I have MgCO3. I've got magnesium carbonate, and I want to see if that's soluble or not. So I recognize first that I have carbonate, and I see that most salts of carbonate are insoluble. Most of these will not dissolve in water, except if my anion is NH4 plus or any of the alkali metals, then that's an exception that would be soluble. Magnesium is not on that list, so magnesium carbonate, not soluble. Sodium carbonate, on the other hand. Now, most carbonates are not soluble, but if your cation is any of the alkali metals, which sodium is, then that's an exception. So that is going to be soluble. Our other major class of insoluble compounds are metal hydroxides and oxides. And so, for instance, if I have calcium hydroxide, CaOH2, that is going to be not soluble. There are, again, some exceptions. The alkali metal hydroxides. So if your metal is any of those, and so something like KOH, that is soluble. Barium hydroxide and strontium hydroxide, they are soluble. And so that's the basics of how we use our solubility rules. We look at the compound, we identify the major components of it, and then we look for something in both of our solubility charts that matches up with part of that compound. And we say, okay, so now is that compound, or is that part of our compound on our soluble list or our insoluble list? Secondly, depending on which one it's on, we then look to see if it's one of the exceptions. And so we'll use that to identify if something is soluble or not. And so let's just look at a couple quick examples. Maybe we're looking at sodium acetate. We want to know, is this soluble or not? And I'm on this chart here, so we'll look on this one first. And I don't see anything on our insoluble list that's going to help us. I don't see anything that talks about either sodium. So again, we have to recognize what our ions are. We have sodium in here, and we have acetate. And so there's nothing on our insoluble list that helps us out. On our soluble list, we see that almost all salts of sodium and all salts of acetate are all soluble. So that tells us that absolutely, this one is going to be a soluble compound. Let's say I have sodium phosphate. So again, we recognize what our ions are. It's made up of both sodium and phosphate. Almost all salts of sodium are soluble. Okay. Let's see if there's anything on our insoluble list, and there is. Phosphate's on our insoluble list. So, okay, well, how's that going to work? Sodium, everything that contains sodium is soluble, but things that contain phosphate are not soluble, except for these exceptions. So remember our exceptions. Anything that contains any phosphate, that contains one of our alkali metals, their sodium is an alkali metal. That's an exception to this, so it tells us that it is soluble. On the other hand, let's say I had calcium phosphate instead. Now, if you're unsure where I got these formulas, the Na3PO4, Ca3PO42, go back and look at all the information and all the resources on coming up with chemical formulas, because that's a very key part. And so if I have calcium phosphate, nothing on my soluble list is going to help me out. There's nothing here that really pertains precisely to either calcium or to phosphate. So I come to my insoluble list. Phosphate's one of my insolubles. Calcium is not an exception. So that compound is going to be not soluble. And there we go. And so lastly today, let's look at how a precipitation reaction might actually occur. And so we have what we call an exchange reaction, where the ions that are in two different compounds are going essentially to switch partners. And so we see here that we're starting with, in our reactant side, with AX and with BY. Now it's assumed that both of these are aqueous. They're both dissolved. They're both in solution. And so the anions are going to switch places. The X is now going to come together with the B, and the Y is now going to come together with the A. And we see that over here with AY and BX. Now, the reason that a precipitation reaction might occur, why we might form a precipitate, is, again, we assume that AX and BY are both soluble compounds. They're both dissolved in water. But now when they've remixed, they've come back together as AY and BX, it's entirely possible that either of these new compounds, either AY or BX, might not be soluble in water. And so using our solubility rules to determine that. And if so, that new compound that is not soluble will come out as a solid. And so here's an example here. Maybe. There we go. And so here we have PbNO3, 2. So we have lead nitrate plus potassium iodide. They're going to react together to form potassium nitrate and lead iodide. And so our two reactants, our lead nitrate and our potassium iodide, were both aqueous. They form potassium nitrate, which is also aqueous, but we use our solubility rules to see that PbI2, not soluble. So that's going to come out as a solid. Same thing with our example down here, barium chloride plus sodium sulfate. Both aqueous, both soluble according to our solubility rules. They're going to come together in an exchange reaction, and we can see that, so the barium is with the chlorine here, but now the barium is going to be with the sulfate. The sodium is now going to be with the Cl. So the NaCl that's formed, soluble according to our rules, but the barium sulfate that's also formed, not soluble according to our solubility rules. And so in each of these cases, PbI2 and BaSO4, those are precipitates that form, which is determined by our set of solubility rules. And so the driving force of this reaction is the formation of that insoluble solid called a precipitate. That's what forces this reaction to occur, is the fact that a solid ends up forming after mixing together two aqueous solutions. And here we have just a few examples of some different precipitates that might form. The first one, we have lead nitrate reacting with potassium chromate to form the yellow precipitate of lead chromate. We have some lead nitrate and some ammonium sulfide reacting together to form lead sulfide in our second example. Our third one is one that I like to do a lot. It's just a nice, pretty color. But we have the formation of iron 3 hydroxide from the reaction of iron 3 chloride and sodium hydroxide. And in our last example, we react some silver nitrate with potassium chromate in order to form silver chromate. And so, deep breath. And I say this probably at the end of every lecture, and I will for most of the semester. Lots of information, lots of stuff here. Digest it. See if you can, make some sense of it. Go back and watch some other, go back and rewatch some material if you need. But where we took things today, just to recap, we talked about some of the basics of chemical reactions and chemical equations. We took that then into looking at the parts of a chemical equation itself and the importance of and balancing chemical equations. We talked about what happens when we dissolve substances and if they're going to split up into their ions or not, because then that led us to then looking at precipitation reactions, where two aqueous substances, two substances that are dissolved in water, mix together and possibly end up forming an insoluble substance as a result, which drives that reaction to occur. Next time, we're going to start by focusing in on precipitation reactions some more and being able to predict the products of a reaction. And so, for instance, when we look here at our examples here, if we look at FeCl3 and NaOH coming together, we're going to look at how we then come up with our balanced chemical formula from that. And so we're going to look at how we go from just our reactants, so how we go from just having these to then being able to come up with our products and balance the equation. And so we're going to look at some different ways to do that. And then we're going to talk about some of the other driving forces and some of the other types of reactions. And that next one, that next lecture of ours will be the last lecture in our first unit. So our first exam is coming right up. And so, like I said, it's a lot of stuff. Digest it. And as always, hit me up if you have any questions. But that is all for today. And I hope everybody enjoys their day. Thank you.